Okay, thank you for the invitation. Good afternoon, everyone. So my talk is about the symmetric capacity and how to use local systems in order to help improving things about the symmetric capacity. So before I continue, let me show how we'll structure the talk. I will first talk about the symmetric capacity per se, and then define the main objects of the study. Then I will talk a bit about the rapid flow cohomology, which is an instrument, a tool, which we will use to aid us in talking about the symmetric capacity. And but the last thing to talk about is the local coefficients and how to use them together with the rapid flow cohomology to find results about the symmetric capacity. So first of all, the main object of study is our symplectic manifolds, which are equipped with an antisymplectic involution phi. And we require the fixed point set is on empty. This is inspired by the cotangent bundle, essentially, and break orbits in the cotangent bundle. We are trying to abstract away the orbits that start and stop with zero velocity or zero momentum. So we are interested in orbits which are symmetric with respect to the zero section of the cotangent bundle. And we take as the defining geometric structure of this of the bundle and the symmetry to be the involution that takes the velocity and takes it to minus the velocity. And then we make this abstraction. You need we pick symplectic manifolds with antisymplectic involutions. Okay, so quick examples of this. We can pick a sphere as two, and then consider the reflection along the xy plane. We can consider torus too, but the torus with reflection along the yz or the xy plane. And these are examples. More sophisticated examples are the cotangent bundle, but we pick sub-level set of a Hamiltonian, which is of the type of potential energy plus kinetic energy, or we can take the lift of to the cotangent bundle too, the lift of a diffeomorphism on a manifold, and then we lift this diffeomorphism to cotangent bundle, and the fixed point set would be the conormal bundle of the fixed point set of the diffeomorphism. This is a useful example for later when we see the local systems. And we'll also talk about some results in the example of the sublevel set of a Hamiltonian of the type I mentioned. But, well, before going on, I will try to say that we have similar results, although this is a different object, we have similar results to the standard simplex topology in this context of symmetric. I will refer to them to these manifolds that are symplectic manifolds together with an antisymplectic involution as symmetric manifolds. Okay, so we have similar results to the standard case. In this case, regarding the easy context of dimension 2 surface. Okay, we have that the area determines the symplectic type in dimension 2. If we have the existence of a equivariant diffeomorphism, we have the existence of a symplectic equivariant diffeomorphism too. But well, there are interesting things to be said, but I can't enter into much detail here. Let's talk about the capacity directly. Okay, so I gave the explicit definition of the capacity in the slide so that I later can superimpose the definition of the symmetric capacity. But I can't explain the motivation, but the Hofer-Zehnder capacity is defined as the supremum of the values of Hamiltonian satisfying the conditions, right? There are differences from definitions. So sometimes people require, instead of H being constant equal to its maximum outside the compact set, they require it to be zero, right? To have compact support. It's just a matter of translation and different conventions, okay? The important dynamic condition here is the last one, right? That every periodic orbit of H is either constant or has minimal period greater than or equal to 1, which is what we usually call, the literature usually calls, to be slow. All orbits are slow, right? They take too much to come back, the orbits that do. Okay, so how we use this, how can we adapt this definition to the context I mentioned previously, right? We can do the following. We consider symmetric simplectic manifold, and we insert in these conditions of the Hamiltonians that we'll take to take the supremum, we insert the new structure that we have. For example, we not only require that H is constant on some open set, but we require that this open set intersects the, here L is just the fixed point set, okay? I'm using L here as the fixed point set. So we require that the open set on which H is constant and equal to 0 to its minimum to intersect the Lagrangian, which is the fixed point set of our anti-symplectic involution. We, instead of requiring periodic orbits to be constant or have minimal period greater than or equal to 1, we consider we require only the break orbits too. Where break orbits, I mean orbits that connect the Lagrangian to itself. Start and end in the Lagrangian. Here we could take, it would make more sense. We can, if H is symmetric, is invariant, sorry, with respect to phi, we can take a break orbit and continue it to conclude a periodic orbit. It could make sense, instead of taking the period, to take the time that it takes to come back. But this would insert some factors of 2 in some places which may be inconvenient. So take the period of this closed periodic orbit associated with this break orbit. But to go on, we now require the Hamiltonian to be invariant with respect to phi, which is expected to be a relevant condition. But we also require that H assumes all values possible, since it's greater than or equal to 0, and 0 L, it has L, it attains 0 somewhere, and it attains the maximum outside K. So we require every value to be attained in the Lagrangian itself. I should say that this definition, without this condition, was given, for example, in a paper by Liu and Wang. They define the symmetric capacity, but they don't impose this condition. The problem is that without this extra condition here, some degeneracies start to occur when M is not compact. When M is compact. If M is compact, then it ends up being that the capacity without this condition is infinite, is always infinite. So this condition is useful for restraining the capacity in the compact case. Take note that if M is not compact, and for example, L is connected, then this condition is trivially satisfied, okay? But if M is compact, then we have to impose this condition. In fact, this condition allows us to prove a similar result to the well-known statement that the capacity is equal to the area in dimension 2. This is also true in this context, but we need this condition. To give a quick rundown why we need this condition, essentially, when you prove that result, if you remember, when we prove that result, we need to parameterize a region with by going through the energy levels of the Hamiltonian. And since we are talking about break orbits here, not only periodic orbits, we must require that these energy levels intersect all in energy levels intersect somewhere the Lagrangian. Otherwise, this condition would guarantee nothing to our argument. Okay. But okay, this is the definition of the symmetric capacity. Now let's talk a bit about, let's make some comparisons so I can introduce you to the rapid flow homology quickly, okay? This kind of tables are useful when we talk about different kinds of homology. So in Morse, for those who know Morse homology, in Morse homology, we have the space M, or our manifold M. We have a function with just a function in the space. Of course, we impose some conditions on the function, and we require some additional extra structure like a Riemannian metric to define the gradient, so we can create the chain map. But okay, we have a function on M, and then the generators of the chain complex end up being we can construct a chain complex with the generators being the critical points of our function. The chain maps will be the boundary map will be given by the boundary map will be given by the gradient flow minus the gradient flow, depending on the your sign conventions. And this gives Morse homology. For flow homology, we, instead of the manifold, we pick the Phillips space of the manifold. And our functional is given by this, right? This is related to the symplectic form, and this is the part of the Hamiltonian. Here I'm picking a capping disk, and in order not to enter into much details, and I'm assuming that the manifold is very well behaved, it's spherical, it's certain class 0, it's for certain class 0, etc. But okay, and the chain complex generators will be the periodic orbits of the Hamiltonian flow, right? In rapid flow homology, we will have a Liouville domain. I perhaps should put here a simplex homology, but there's not much space. Well, for those who know simplex homology, the situation is pretty similar. We have a Liouville domain. We have the completion of the Liouville domain. So we have, by having a Liouville domain, we have an exact symplectic form, and then we take the functional. But instead of just a Liouville domain, we now have a Liouville domain with a Lagrangian, with a fixed Lagrangian L. And then the function is this. This first term now enters due to the boundary conditions. We will not only restrict to periodic orbits like the Phillips space, but we will pick orbits that begin. The space will be constituted of orbits that begin on L and end on L. And this function f that appears here is related to the form, the symplectic form. In what way? Our symplectic form is exact, so it's d lambda for some lambda, and we will require that this lambda will be, when restricted to L, exact too. So this lambda is on L equal to df for some f. This f then is a function on L, okay? And then we evaluate the f on the beginning of on the end of the path and subtract it from the beginning. This is the functional, and the chain complex generators are the break orbits of the Hamiltonian flow. The chain maps will be like the flow, similarly to the flow homology, will be those generated by the flow equation, right? The moduli space. But this gives us an insight, right, on the space and on the functional. And I need you to understand both this space, the space of paths between that start on L and end on L. And it's useful to mention this function f here. Why? Because we have the main results relating to the capacity, okay? We have the result that if we have a symmetric Liouville domain, symmetric in the sense of the existence of that evolution, satisfying the conditions for the definition of the rapid flow homology, right? Of course, there are, like the Morse homology, which has conditions on f to be defined, there are conditions on the Liouville domain in order for us to have a rapid flow homology, okay? But I'll not enter into those details. But the point is, what is important here is that the f that appears here in the functional, that f is constant on the completion of L minus L. If that's true, and if this cohomology class here is equal to 0, then the capacity is bounded by A. What is this cohomology class here? This cohomology class is when we look at, there is an isomorphism between the cohomology of the Lagrangian and the rapid flow cohomology given a small frame of, when we filter by some small action. It's similar to the case of flow homology. When you have a C2 small Hamiltonian, the flow homology is isomorphic to the standard homology, right? Similarly, we have the same result here, but it's important to note that we do not have the homology of the space anymore. We have the cohomology of the Lagrangian. But in any case, we have the canonical one on the cohomology of the Lagrangian, and we look at who is this canonical one in the rapid flow homology when we filtrate it by the action of by those orbits who have action greater than or equal to minus A, or smaller than or equal to A, depending on your sign conventions. So who is this canonical class? Is this FA. So a simple case of application of this result is when, instead of knowing who this class is explicitly, we just know that the rapid flow homology vanishes. If it vanishes, then the capacity is bounded by, it's finite, right? It's finite. Okay. So the usual, I can't enter in the details of the proof, but the proof of this uses the concept of spectral invariance, and it's inspired by the proof that can be seen in a paper by Iri, for example, of the similar result in the case of periodic orbits, but this condition doesn't exist there, of course, the F is constant. This condition is not too restrictive, okay? For example, if the boundary of L is connected, this is true, because there are conditions on F such that the fact that near the boundary, the dF is equal to 0. Okay, so it's locally constant already. And if we are considering the cotangent bundle, it's already 0. It's already constant either way. So, okay. So we have a result stating that if the rapid flow homology vanishes, then the capacity is bounded. And the capacity has a lot of applications to dynamical purposes, okay? The capacity is related, for example, with an existence of periodic orbits in a full measure set. And just like the periodic case, there are these results in this case too. So for example, before I start talking about local coefficients, let me explain that there are results, for example, where we know the rapid flow homology vanishes, right? Another paper by Iri proves that if we are on that case that I mentioned, that we are in the sub-energy sublevel set of a given Hamiltonian, that is the sum of potential energy plus kinetic energy, and if the level set intersects the zero section and the sublevel set is connected, then the rapid flow homology vanishes. He uses some arguments about Reunião section to prove this result. But in general, it's not easy to see that the rapid flow homology vanishes. It's not easy to compute this. So we try some other strategies. Instead of computing directly the rapid flow homology, we can try to impose local coefficients such that the rapid flow homology vanishes. What's important for some technical reasons is that when we restrict these local coefficients to the Lagrangian L, these local coefficients restrict a trivial local system. Okay, so in essence, we are searching for local coefficients for which the rapid flow homology will vanish, and such that these restrictions of those local systems to the Lagrangian are trivial local systems, the standard homology. So for those, I can't explain, sorry, the basics of local coefficients, but we essentially, we can, for those who know about holonomy, it's related to holonomy, but we have a module of coefficients, and then we investigate how those coefficients can change, what going through a loop can change, how can it switch coefficients, right? So this intuitive meaning I just said may justify why we are trying to investigate the space of homomorphisms of the P1 of the space of paths to some group G. This group will be a subgroup of automorphisms of some module, okay? We are considering G to be a billion here in order to ignore if G were not a billion, then we would have to take a quotient by conjugations. But we are trying to we're trying to investigate this because these are elements of this group, this space of homomorphisms are the local systems of coefficients. So what is our expectation? We try to impose, we try to find conditions regarding the homotopy or homology groups of M, or L, or both, or relative groups, from some kind of topological conditions of them, such that we find a local system for which the homology vanishes, and that when we restrict this local system to L, it is just a trivial local system. So let me explain briefly how this strategy was taken by Wunsch, from Felder, and Albers in a paper where they make pretty much the same thing, but for the case of periodic orbits. They pick the longest exact sequence of associated with vibration, and they have the vibration of the base loop space, the free loop space, and the space M. The crucial thing that helps that analysis is the fact that this vibration has a section. We can embed M in the free loop space by taking points to the constant paths. This provides a section for us in the long exact sequence, which helps prove to put some more structure required for a meaningful discussion to happen. Here we don't have this vibration, this section. What is this section intuitively? This section requires us to given 2 points on L to find to provide a path that connects those 2 points. There is no way to consistently do that for any M, L, and L. Okay. So there's no canonical choice of path connecting both. But there are conditions we can impose that make the section, that guarantee the existence of such a section. For example, if we suppose that this inclusion of L on M is no homotopic, we have a section. We can just pick the point, the beginning of the path, and trace it. We can just take one point and trace it, the contraction to the point that, well, it contracts, and then trace it back to the other point. I have a picture to illustrate this. So, for example, consider S1 inside S2. S1, of course, is not it is no homotopic inside S2. So we can, for example, take S1 and contract it to the North Pole. So given 2 points in S1, we can just follow the contraction in half the path, and then take the reverse path to take us to B. So this provides us a section in this, when we have this hypothesis of the inclusion being no homotopic. So furthermore, not only we have this section, but the fact that the inclusion is homotopically trivial makes the action to be the identity. And as you may recall, the existence of a section is not sufficient for the middle of exact sequence to be the product of the less and the side parts. Okay, it's a semi-direct product, but in this case, due to the action being the identity, it will be a product, and this being a product is important for some technical reasons, which I may explain later if anyone is interested, but I can explain now. But but okay, this is a product, right? So we have that the P1 of the path space is a product of the P1 of the base loop space, and the P1 of L times L. So we can now consider the isomorphism between the space of homomorphisms, and now I'm taking G to be ZL. Okay, we can consider G to be ZL if it considers coefficients to be C, for example. Then ZL lives inside the automorphisms of C. Yes, okay. The projection, now, when we look at this in this destruction of a product, we can now see that the projection on the sacred coordinate corresponds to the restriction of the local system. When we see the element of this group as being a local system, it corresponds to me taking a local system here and restricting it to L times L, restricting it via the pullback by the section. So now let me recall what we are searching for. We are searching for local system of coefficients which restrict to trivial systems on L. If they restrict to trivial system on L times L, by taking the diagonal, they restrict to local system, trivial local systems on L too. Okay, so we are actually we are searching for non-trivial elements of this group. Because as soon as we have a non-trivial element of this group, we can take suppose we have a non-trivial element A of this group. So we can take A times 0, and this will provide us with an element here that restricts to a trivial local system, which is exactly what we are trying to find, okay? So we need conditions that will guarantee this to be non-zero. So let's now do some topological algebraic topology. We can consider the sequence of isomorphisms. I'll try to describe quickly what they are, okay? So this one is just the fact that the homotopy groups of the base of a loop space are related to the loop space of this space by a shift of 1, okay? And we have the P2 of a manifold is equal to the P2 of its universal covering. Simply, you can see this by the fibration of the universal covering. And due to the universal coefficient theorem, we have this last isomorphism. So if this group is not 0, we have non-trivial local systems of coefficients in this path space, which restrict trivial systems on L. But the fact that these are non-trivial, now I have to pull some results. Well, the fact that this is non-trivial local system on this path space implies, in our specific case, that the homology of the base loop space will also be 0 under these local systems. Due to a local version of the Serre-Lehey spectral sequence, it also follows that the homology of this path space will also be 0. Since this homology of this path space is B0, this homology of this path space is related to the rapid flow homology via a similar result that states that the simplex homology is related to the homology of the free loop space of the manifold in the case of simplex homology. Okay, so we arrive at if this is not 0, summarizing, if this is not 0, we can guarantee that the rapid flow homology of the cotangent bundle and a conormal bundle of a given submanifold of M is 0, and therefore that the capacity is finite. So this is an example of an application. We arrive at a condition state where the rapid flow homology will vanish. Of course, it's other coefficients, but it's okay because the result that I mentioned still applies. We found coefficients for which the homology vanishes. Do I still have time?
Still have 2 more minutes.
Okay, so based on this, we can try to ask what other conditions other than the inclusion being homotopically trivial could we try to find? If we go back, we can see that I could say, well, if the P2L is 0 and the P1L is 0, the result will also be true if you think about it a little bit. But this is okay. This is useful, but it's also very restrictive. Are there other conditions that allow us to make meaningful conclusions? Maybe we have to investigate more thoroughly and not suppose that the product is direct, or I don't know. And just to mention a case where we could not find similar results, because maybe by presenting this quickly, it's possible to think that, well, everything seems similar or has some kind of similarity or analog result. But there are results for some displacement energy where we can bound the displacement energy. We can make some bounds regarding the displacement energy and the capacity that I could not find similar results for the case of the symmetric capacity. And the core issue is the fact that when we have two Hamiltonians, HE and GT, this Hamiltonian generates the flow of the composition. And this Hamiltonian, if H and G are invariant with respect to some involution phi, this Hamiltonian will not be invariant. And this breaks down a lot of the algebraic structure for those proofs of this displacement, the bound of displacement energy. Analytical arguments break down, and some dynamical approaches of breaking down the paths in 4 parts, etc., also break down. So this is something that I was not able to investigate with respect to the symmetric capacity. And sorry if I went too fast on some parts. This is the presentation. Thank you.